which corresponds to about 3 to 5 kilojoule per 0.1 gram of palladium cathode. They also observed some sort of correlation between heat and neutron production, which is illustrated in this picture. They measure charged particle spectrum, and they observed the upper limit for energy of charged particles about 20 MeV. And they also observed some sort of post effect for about 10 minutes, but the authors themselves stressed that these results needs further investigation. And they also measure spectrum for various cathodes, and they observed lights which correspond to some transition between different nuclei. For example, for palladium of this type transition, which can correspond to this reaction of Cape temperature. To check the results of this last group, another group from Tomsk Institute of Nuclear Research performed experiment with nuclear discharge. They used palladium foils and they measured neutrons and charged particles. They did observe bursts of neutrons during discharge. It's not so bad, and the real picture may be a little bit different.
What I'm wondering is, could you give us the absolute temperature for that too? I'll get you together with you later on that.
So the temperature of excessive heat?
In other words, was the baseline room temperature or something like that, or was it the baseline temperature of the car?
What experiment?
The car low discharge neutron.
Let me see. Maybe there is some.
Maybe you just go back to that slide, and I can. I'll catch you later on that. But the other thing I wanted to comment on was the Zelinsky data from Kharkov University, and there.
It seems to me it was about 700 Kelvin. I'm not precisely sure because it seems to be. Yeah, that's right. No, not high. Podolsky experiment, as I understood. Did you ask me about Podolsky experiment? Which? Karamov. Yeah.
The other question, I'll check with you later on this, but the other question was this, I guess it's a comment, but in the Zelinsky data, it looks like the neutron emission would be correlated qualitatively with the thermal absorption of the neutrons of the films, but that is fairly good in the case of, I guess, the palladium, but not so good in the case of the titanium, just the reverse of that. So I don't think that that would be the whole story in that case.
This is a question.
And you work that one out, the variation of fugacity of the diurnal potential is e to the minus 2 eta is diurnal potential f the Faraday over RT. Well, eta is always negative for hydrogen diffusion, so that's where you get your relative pressure or fugacity. That's where you get up to 10 to the 10 and 10 to the 15 even more for the values of open potential which we observe, which are around about 0.6, something like that, 1 and the square centimeter. Now, as you go to other methods, you see that you get quite different expressions. And the two that are going to interest us, which I'll give you some evidence, are these last two. So I'll say just a word about what a couple of discharge combination mechanisms would be. That's where discharging plus E absorbed H is rate determining, but it's coupled with a combination which happens at the same speed. There's no back reaction, but this is the rate of set. And then you get into the minus e to f over 2 RT. You immediately see this will be vastly less in fugacity because, of course, it's in the exponential. The exponential is 4 times less. That's going to be a heck of a lot in respect to fugacity. But then there's another one, the coupled discharge electrochemical desorption. Instead of combining H plus H to give you H2, now the hydrogen is got rid of by H plus coming down on the absorbed hydrogen, combined with the supplies there, right off to an H2 or a D2 of course. And now we're back again to high fugacity, but there's a star on this. And it turns out that what that star means is that you only take the open potential, not the experimental value now in this mechanism, but only to the value at which theta, coverage with hydrogen, fraction coverage with hydrogen, becomes 1. And once you've got full coverage of the surface with hydrogen, it doesn't produce a deuterium if you wish, it doesn't matter what you do, stream away to another 10, 20, 100 times more current density, and it won't change the fugacity. So now we've got that in a graph here which shows you dramatically the difference between the fugacities you get in various mechanisms. And all you need to see with this one is that with the coupled discharge combination, it's low, relatively low. Say we're at 0.4, then up here we'll only have 10 to the 3 or 10 to the 4 atmospheres for the fugacity. That will be, you might say, just what fugacity on what? It's H2 or D2 in voids or cracks or something inside, and that, of course, then affects the activity of the atoms, which make up the dPd ratio. But suppose now you keep your open potential, you change mechanism, and you go up to this one, the coupled discharge, you suddenly find you've increased your fugacity from, say, 10 to the 3 to, say, 10 to the 10. So you've got a huge increase in fugacity by changing mechanism. No twice or 3 times, but 4 orders of magnitude. So you can see then that knowing, if you want to know dPd ratios and why they're what they are, and how everything which affects the surface reaction may affect the dPd ratio and the actual activity and pressure inside, you have to know what's the mechanism occurring on the surface, because you get such dramatic differences depending on what that mechanism is. Well, now we talked about stuff on the surface. Well, that implies there's something inside. Indeed, it's the stuff inside that we always talk about. And one of the things I promised Effie to do too is to measure the solubility of the hydrogen as a function of the potential on the surface. And then whilst I was preparing this lecture, I remembered that long ago I had a graduate student who did a little bit of this. And so I reproduced something of his work here. I wasn't going to show it in the slide, that's why I drew it out by hand. But essentially it's correct in the slope and the intercept. Here's log of CH, that's the atomic concentration of hydrogen in palladium. This is the open potential. It extrapolates zero potential to 10 to the minus 4 moles per liter, moles per cc. And that's a very verifiable figure, because of course you can just take palladium and have hydrogen gas around 1 atmosphere, and that should give you the same value as the extrapolated electrochemical value that you're getting by finding the permeation value of the hydrogen through palladium and so on. So you've got to check on it. It comes out to about 80% right. It's not an exact verification. D log CH by D eta, how much increases the slope, came in this chap Fullenweiler's work to minus f over 3.4 RT. Now that's a bit of a shivery value for electrochemists because they like nice integral values, and the integral value f over 4 RT makes a great deal of sense for us. And so I'm going to fudge a little bit and take this 4 RT in deciding what this implies for the mechanism. If I convert this CH to fugacity, FDH2, I get d by d eta log FDH by d eta is minus f over 2 RT, and now I want to put back the thing where I have the fugacities and the open potentials. And you see there's only one which would correspond to that. It's this one, 2 RT over eta f. So, for what it's worth, I say that because it's only one method of approach, and a paper which is more than 12 years old, the indication might be that the low current, near the reversible potential, coupled discharge in combination may be the mechanism. See how that fits other data we're going to get. Well, as we start talking about the solubility of hydrogen, how it increases with overpotential, we can easily calculate when the dPd ratio should be 1. And it comes to a rather low value here, potential, thank you, a rather low value. If you take the values which we got in those days, and you extrapolate the dPd equals 1, you reach it at minus 0.24, minus 0.24. Now mind you, we're often working at minus 0.3, 0.4, sometimes even minus 0.6. So it would seem that we're pushing into dPd equals 1, where a lot of us find it difficult to get there. Well, I'd like to follow from this to a small consideration of cracking. And you might think that to indulge in a little bit of lecture on cracking all within the auspices of 45 minutes is a bit much, but I'm going to do it very, very simply and take what is called the Griffith crack. The Griffith crack is a good old crack. It's a very elementary cracking treatment. It assumes that the crack is elliptical, and you assume that at the beginning, when the gas, which of course plus would be D2, gets into the crack, that the crack is intrinsically there. It's called the void within the metal. This void is there without the entrance of the gas. The gas gets into it, and of course, if it gets high enough pressure, the crack will begin to spread. That becomes officially a crack. It's a void that starts to spread and get dangerous. And at the time that it's only a void, then you can show that 16/3, that will vary the exact shape of the crack, Young's modulus times the surface tension over the length diameter of the crack to the half is the pressure which is going to make it spread. Well, I'm fairly confident about my Y, which I looked up and got a recent value, my gamma, which I looked up and got a value fairly recent, but my L, of course, is a speculative value, and I had to put down there at what was a little better than a guess. I know that in iron there are intrinsic voids which are about 1,000 angstroms long. And so I've taken that without any direct evidence of palladium having such voids. I put it down here and I've calculated the pressure which would form, begin to make a crack move, or a void move and become a crack. And on those bases it came to 6 times 10 to the 3 atts. And if then I take the fugacity of 10 to the 4, which corresponds roughly to the overpotentials I was talking about, I get 2 times 10 to the 3 from Bockris graph. So you see, at the minus 0.3 overpotential, which is, we're going to show a change in mechanism occurs, we're fairly near to cracking already, or at least fairly near to a condition which thermodynamically says a crack will begin to spread, because if I calculate 6 times 10 to the 3, and don't forget I'm a little shady on what that value could be. This is 2 times 10 to the 3. We're precious near, not enough to crack, but quite near the conditions. And in a minute we're going to show the overpotential goes far above that. And so the indications are that cracking is a kind of very intrinsic difficulty, and it's going to be very difficult always to avoid. In fact, there are 2 counter things. Practically all of us say that dPd equals 1 is good. We want to obtain that, and yet we find that it's going to lead us towards cracking. Well, now let me present very briefly the other work we've done so far on mechanism. This is Dinescu's work at Texas A&M. There's a typical, what we call galvanostatic or constant current transient. We put onto the palladium, and this palladium, I must be very clear with you, is young palladium, not yet done the palladium that corresponds to, say, 2 months electrolysis. It's a much more difficult thing to do. This is what you might call normal palladium, where you prepare it, you clean it, you put it in a solution, and make the measurements over an hour or 2. That's the kind of palladium this is. And it has its own problems, as we shall see. And so the over-potential goes up and comes to a rise time, the constant part, which is a few hundred seconds, 100, 200. Well, now, that provides us with a problem in our mechanism first, because, you know, we've already said that it's going to be this discharge coupled, this discharge combination, because you can calculate what the rise time ought to be. It's a very simple calculation. It's just 4 times C times RT over F divided by the current density. And that formula, by the way, comes into all kinds of electrical engineering, too, apart from electrochemistry. Just considers a double layer condenser as discharging. And you then take, quite uncontroversially, 50 microfarads per square centimeter for the palladium surface, and we're talking about a milliamp, 10 to the minus 3 amps. It works out 4 times 10 to the minus 3 seconds. Well, that's a bit of a discrepancy that you can't allow to go, because the rise time is really 100 seconds, you see. So we had to think about that. But I think the thinking about it is very simple. You see, Zora Minestes, my student, has a 25 micron thick piece of palladium, foil, palladium. I think that's what's happening. I think it's just diffusion through the foil. And when you do delta squared, which is 2 Tor, the simplest way of treating diffusion times, and you put 5 times 10 to the minus 8 diffusion coefficient, you get 62 seconds. For the rise, we get 100. So I'm not very worried about the discrepancy now. I think we can let that discrepancy go. So now let's look at what we call in electrochemistry the Tarfel lines. And Tarfel lines are electrochemists, PV equals RT, you might say. They're the sort of standard electrochemical beginning of the technique of looking at mechanisms. And what they are plots of over-potential, the deviation from the reversible potential as a function of the rate. So here we go, 10 to the minus 5. We go up here and we get an excellently straight Tarfel line. That's what we want. We want a linear log I graph, semi-logarithmic graph. And then we get a very sharp break. Another Tarfel line. It has quite different properties. Now, the theory of electrochemistry, electrokinetics, says that this kind of Tarfel slope, this B, this gradient, log I, is quite reasonable. It's a bit high. In theory, it says it should be 127. At this temperature, and it's 157, but such deviations are not unusual, and we should count it as green with the theory that I suggested earlier in solubility. But to explain 357 all out, you can't do it. 357 is far too high. And electrochemists, however, for quite a long time now have been explaining very high Tarfel slopes you sometimes get as indicating adsorbed material, absorbed impurities on the surface. So when we saw that line, before we did our XPS or analysis of the surface I'm going to show you, we immediately said, aha, that means it's a very dirty surface, and we've got stuff there, which is muck, going to spoil off the line, and we can even do a calculation about it and show that if the stuff, the muck, has a dipole moment of something like 2 pi, a reasonable dipole moment, then it's it fits in with the slope of about 330, 340, so we believe that it rationalizes it, it doesn't prove what causes it. Well, now, we're certainly not through our mechanism work. As I say, it's still on rather young surfaces for cold fusion work, but here's where we are so far. We think that up to the form of that break, up to the break of the lower current densities, up to the break of the Tarfel line, D plus E gives you deabsorbed. 2 deabsorbed is going to D2, combining. That would mean that the theta D, the coverage of the surface, would be much less than 1, 0.1 or less. It would also mean the fugacity of the break would be about 10 to the 4. But Gauss's graph tells us that the solubility then would be about 2 times 10 to the 3. But when we come down here to the after the break, we go up to that higher Tarfel line, it's very probable, not proven, it's an inference, that we've got on this other mechanism, the so-called electrochemical desorption. Of course, you've still got the discharge of the proton, but now it's right up to theta equals 1, and so you get the proton, the deuterium off by D plus deabsorbed, it hits it, strikes it, desorbs, the electron comes, D2 goes up, and it implies that it's fully covered with deuterium, that the fugacity is whipped up tremendous 10 to the 10, but for Gorski, the solubility is still very high, but not too bad. It hasn't gone past the 10 to the 4 mark. So that's the preliminary estimate we have on the mechanism of deuterium evolution on palladium right now. What we still have to do to be much more sure, two things, I think, both within our capabilities in our laboratory. One thing, the main thing, and I had very much hoped to bring to this meeting, but it just didn't work out. Didn't get it done because the machine is new and still has breathing troubles. It's the Fourier transform infrared spectroscopy, which we can apply to surfaces in solution. We already have a paper out on doing hydrogen on iron, and we are trying to do, we will be trying to do this week, the hydrogen on palladium. And what you do is you watch the vibration of the stretching vibration of H or D on, you do it both, because then you get the isotopic effect, make sure it is hydrogen you're looking at, of this bond on the metal, and you see how the area of the peak varies with potential, and then you can calculate later and see how it varies with potential, and that's very diagnostic. There is various ways depending on what your mechanism is. So give us a good test of this. And another test we can do is to do the permeation of deuterium through palladium as a function of the overvoltage. There are several expressions in the literature which show that d log p, the permeation, d eta, the such and such and such and such various coefficients. These coefficients are clearly related to mechanism. So those two tests or two model experiments should get us clear. We can do them, of course, in the older relations too. Well, now I want to talk about the surface. We've been doing quite a bit on this recently. Surprising results, obviously, rather shocking in many ways. This is the most shocking one. This is old surfaces. The surfaces, no, they're not old, sorry, old surfaces in a minute. These are surfaces which have been annealed to 800, cooled in an argon atmosphere, and then found to be largely carburized, presumably from oil from the pump or something like that. It hasn't got through the liquid air filter, but there's a very large, thick, 5 micron surface which is 70% carbon. When we put that in the solution, it looks rather grayish, and turn on the current, then after a little while it detaches itself from the surface, falls off, and a very bright, shiny palladium comes, which nevertheless itself within 1 hour has 2% platinum in the surface. I'll give you lots of graphs on how platinum varies with thickness and time in a moment, but before I go further, I just want to talk a little bit about that platinum. How it got there. Because it's an awful lot, 2% platinum in the surface deposited in 1 hour. And, well, this is a little bit of pure electrochemistry. You calculate the carburized section. The total moles of the carburized section is 3 times 10 to the minus 3. And you go down and apply Faraday's laws and find out that the partial current density for the platinum is 2 milliamps. Of course, the overall current density is 1, so it's still only just over 1,000 of a partial current density. Pretty surely far too high for a reasonable amount of platinum in the solution. How could so much platinum get into the solution? You ask yourself, calculate how much. It's 10 to the minus 4 moles per liter. You can measure it, it comes near that. This should be 5 times 10 to the minus 5, as a matter of fact. And I think the only way to explain it is not in terms of the solution. You might be surprised at that. You might think noting the solution is the obvious mechanism. But when you do the calculations on that, it doesn't come out very well. The standard potential for platinum dissolving is 1.2 plus. If you had an acid solution, you'd have plenty of overpotential to dissolve platinum. This solution of platinum acid solution is very well known to the plane of electrochemistry. But in alkaline solutions, you're very negative with hydrogen solution. The reversible potential is right down to minus 0.4. And so to get right up to plus 1.2 on the anode, you've got to have an awful lot of anode voltage. Now I take that into account. I reckon the anode potential 1.4, which will give you very little overvoltage to drive the platinum solution reaction. So I'm suggesting that probably oxide breakup. There's a 5 or 6 layer oxide film on the platinum. And I suspect with this very, very vigorous evolution we have to do in cold fusion, that it breaks the oxide up off the surface and pushes it into the solution, perhaps even colloidizes it, and that's the reason for the terrific amount of platinum. Well, now we did our XPS, and we did it at various depths, and here's some quite interesting results which came out of it, you see. Let's just read this graph and show what it means. Concentrate on the platinum, perhaps. Here's 1 hour, 1 day, 1 week, 3 weeks. This is referring to the electrolysis time. This is the examination of the cathode, which has been interrupted after these times here. And this is the depth and angstrom that the XPS, the angle result XPS, was taken to. So you can't see much after an hour, but after a day, it's already up to 10% coverage. And after 3 weeks, 60% of the surface is covered with platinum. And then down to a depth of about 10 angstroms, almost the same, falls off exponentially, but you can still get registrations of the platinum with XPS through 70 or 80 angstroms. So you see, there's the first real solid evidence we've got on all 4 platinum there. Silicon, lithium we did by Sims as well, got results down to 4,000 angstroms. There's a tremendous amount of lithium there, that is well known, but the silicon, and we have other results, copper, zinc, all show that there is an enormous amount of impurity present on the normal type of cathode. And I think that we have to learn a lesson which Dr. McCoubrey has taught us, or has been speaking about for something like a year. Fritz Will has taken it out and used it in his apparatus. And I think I'd like to, although I haven't been doing it myself, I think I would like to say that that's the way to go, because this vast amount of platinum here does not work on the palladium surface at all. And the platinum will lower the open potential there, and I think it's altogether deleterious. And a fuel cell anode, 2 or 3 people have spoken to me about this and made clear they didn't really know what that was. It's very easy to explain. You simply put the deuterium anode, no oxygen involved, no reactions, D2D plus 2E, I think will explain that. And you just get the deuterium dissolving, no oxygen, of course, it evolves on the cathode. So it's a 2 advantages. It doesn't give you any platinum, it's going to go up to higher voltages to dissolve. At the same time, it prevents any question of oxygen combined with deuterium, which is one of those terrors of cold fusion work. Well, for those of you who know my papers here, know that I've been talking since about May 1989 about dendrites, and I just want to show you that they are indeed there. Oh, indeed they are. There they are. This is masking interference spectroscopy or interferometry and interference contrast microscopy to be precise. And you see, not only are there 2 obvious superdendrites, so to speak, which are about 2 microns high, but there are obviously loads and loads of little ones here, which may well have the types of radii curvature, about 100 angstroms, which is needed for the acceleration type theory, which Kim, the University of Illinois, has been developing, partly, I think, on the basis of what we suggested way back there. And it's one of the mechanisms, one of the 4 mechanisms, I think, which we should consider in cold fusion at this time. Well, part of our effort duties bring us into looking at the solution too. Our work here hasn't finished. We've got a reactor at Texas A&M, so we can do activation analysis all right. We've got an inductively coupled plasma machine which does the analysis very, very sensitively, very, very quickly. But I'm afraid that our results here don't agree. They do agree qualitatively, they don't agree within 5 times. So that's why I'm saying we haven't finished this yet. But for what it's worth, in the middle of the work, as it were, here's a graph, and you can see that, well, perhaps not unexpected, there's the tremendous climb in silicon, a very big climb in platinum, and a climb, though I don't know how to explain that, fall later on, in several other things, zinc, iron, copper. It's a good question to ask where the name and fortune these things come from. Of course, the silicon and the platinum don't need discussion. I think the zinc and the copper come in the following way. You see, we have, of course, our electrodes sealed into glass, and then, perhaps rather stupidly, inside the glass, we connect them up with copper. And I think these seals leak. I think that's the only explanation I have of where the copper comes from. Well, of course, it's easy to stop that and put another type of material there that won't leak and look after it. So that's the thing we can cure. Before I go on to the last part, which is about the heat, I'd just like to say, how could we get a super pure electrolyte and get rid of all this? Is it within our capability? I think with a fuel cell anode it is. I think without fuel cell anode it isn't. I looked into, worked with, acquired phone colleagues and all sorts to see what other anodes might be available. Ruthenium oxide on TiO2, peroxide. These are all very non-dissolving anodes which people tout. But once you get to 1 amp per square centimeter, that's nothing much. It really is very destructive. And if we're going higher, on sometimes said go much higher current density, it would be much worse. And so I don't think there's any chance of getting non-dissolvable anodes. They're all dissolve or decrepitate or split or do something to get the stuff in the solution, and they end up in your cathode. So I think we've got to avoid that completely. But of course there are lots of other things. The silicon, well, what about a Teflon cell? There's much to be said in favor of it. Some details should be added that I haven't time for. And in the end, we could really circulate the electrode and scavenge it. That is to say, we take the solution out and constantly push it through a number of ways which electrochemists have to remove things from the solution. So I think it can be done. It's expense and time. Okay, well, part 3, watching my time now, is on to the heat. So I'll be very quick on the cell. The only new feature this has is that, well, not a new feature, but we sent one of our chaps to Dr. Fuga's lab, and he kindly instructed us in DVD ratio by the resistance method. We use it. Up here is our combiner. The stuff comes back here. We can switch it over to the tritium here. That's the circuit for the measurement of resistance. We measure follow resistance continuously. We have a fully automated electronic computerized setup, so at any moment we can press a button and look at the DPD in any cell. Calibration, not going into it in detail, because so many people have done. We calibrate very frequently, but if we see any heat, of course, we recalibrate once. Every cell gets recalibrated in this big way once a week, although it takes several hours. We try to get different people to do it, but there might be a subjective factor there. So we bring in the other students and let them do the calibrations themselves. One thing here is that when the cells, those that have bursts, finish their bursts, they do go back on this line and evolve classically. So I think that's a very good indication that the film part, calorimetric part is okay. We have a man called Ken Marsh at Texas A&M who is a sort of professional calorimetrist. There aren't very many of those nowadays, electrochemical calorimetrists who work with light sort of heat measurements and electrolytic solutions. And when we brought him over and said, Ken, you've been doing this a long time, tell us what's wrong, he roared with laughter. Hey, with all that heat, you don't need the skill of calorimetry. So he's very contemptuous of it all, and he said that they could do fantastically much better. So after his ridicule, I haven't taken too much notice. We do have some difficulty with the stirrer. When the stirrer changes its velocity, which it does sometimes, then it affects the temperature. We have to be extremely careful about that. That's the graph of stirrer speed versus temperature. And of course, one is afraid of false results. These things all go during the night. Texas A&M has its own electricity works. Suppose they change potential during the night, etc., etc. But you see, if there's a speed up, the temperature drops by 0.2 degrees or something like that. So it's only if the stirrer stops that we get a pseudo-burst. And the pseudo-burst is very great. Most of our bursts have been measured during the day, and of course we can see the stirrer. Well, here's the thing, that of all the things I want to tell you in this lecture, it's the one that is perhaps the one I want to show you most. The line that we're going on correctly here, the heat particle, Dr. Hodgkin, by the way, over here, so I'm in SD on the other stuff, is pulsing. And the long program is electrical, mechanical, and heat pulsing, with the heat pulsing work right now. I don't think I have time to describe all the plans we have for it, but the ones that I'm going to show you are pulsing at 2 amps per square centimeter cathodic, 5 seconds, and then go to 0.1 amps per square centimeter anodic, 5 seconds, and up and down, up and down, up and down, up and down. Well, now we've completed only 4 complete runs over 1 month of pulsing. 4 cells. And 3 of these cells, we did the pulsing, we got no heat, and the DPD ratio did not change during the pulsing. But 1 cell had a DPD ratio which went right down during the pulsing. Here's the DPD ratio, which was the start of 0.83 or whatever, 0.84. And over a lengthy time, something of the order of 19 hours, it went right down to 0.2. Now, I think you can understand that as a free dissolution of the deuterium cathode, because clearly, when it's going to be a cathodic, most of the stuff is just absorbing E2, but anodic, most of that current will go to draw the D up. And so that is what you'd expect. And when it doesn't happen, I think we're just suffering from blockages manifested by the XPS. And then when we got down here, we went into rapid charging and immediately got heat to the extent of about 10%. We have heats up to 19 or 20%. This is 1 burst. We had 5 bursts in the recent work, and you see this particular burst lasted quite a long time, 2 or 8 hours to something like 240 hours with those variations. During this time, of course, we were not pulsing. And the burst was interrupted by renewed pulsing. It would have gone on otherwise further. And here's the whole lot of the bursts in this particular electrode where the pulsing caused the D to sweep up. And there's very interesting things. I mean, we could talk about these bursts for perhaps 10 minutes because there's a lot of structure on them. And you can see there's a rough tendency, this is over a rather large time, about 300 hours, 2 weeks, something like that, to go up. The pulses increase. Pulse, small pulse, bigger pulse, small again, bigger, 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 as time went on. And the next table shows you to what extent we interrupted them, to what extent they ran out of heat steam, as it were. The first 3 were interrupted by more pulsing, and the last 2 just stopped. They stopped after a rather long time, 12, 20 hours. And why they stopped? Well, of course, I speculate, but perhaps when you discharge anodically, cleaning up the electrode, you're getting the stuff out. When you put it back again, it's fresh, it's good, it happens, the effect occurs. But of course, there's always a little water. We check this with NMR, but there's always 0.2, 0.3% water there. And the water, the poison, goes in gradually, and perhaps that's the end of the burst when it sets up enough. Well, finally, on these bursts, then look at this energy per mole. This is megajoules, and so when you add them all up, 39 megajoules, that's about 100 times the heat of sublimation. Now, it's not as much, anything like as much as Fleischmann and Holmes have reported. They reported far better than this, but it's still a remarkable figure, and of course, it's part of the argument. It's nuclear because of the fact that it's so much more than anything you could possibly imagine chemically. By the way, I think I should change my way of doing things because of the work of the presenter yesterday, Dr. Leo, who compared everything with D2, the oxidation of D2. I think that's the way to go because D2 is fuel related. Okay, well finally then let me tell you what my conclusions are, and it's pretty easy to say what they are. Not only is palladium thickly encrusted with impurities, particularly platinum, they penetrate about 100 angstroms thick, far more than lithium. And this all happens after a few weeks. So many of our runs go on for a couple of months. Surface is indeed dendrite covered, as many of us have said. I hypothesized and worked with. Mechanism of surface reaction seems to change about -0.3 anode potential. Fugacity would, but it's of course a deduction, it's not a proof. Increase greatly at that point, and the pressure will go into a crack spreading pressure and a changing mechanism, and you'd expect cracks. The condition would be positive for cracks to spread. The probable mechanism in regions of interest to us in cold fusion is what chemists call, electrochemists call, the hierarchy mechanism. And what that means is that D plus discharges forms a full complete layer, and in order to get HD2, more D plus discharge on top of it absorb D, and it goes off directly to D2. That's the hierarchy mechanism. Electrical pulses of about 5 seconds in length sometimes, when they cause the decrease in the deuterium inside, trigger heat bursts, which then last for many hundreds of hours if you go on pulsing. And I think that the key point is the surface contamination, and I suspect that it is the cause of the major difficulty in the field, which of course is irreproducibility. And so I think we may be very much further on if we really can attain clean electrolytes. Thank you. Speak about it, but he's been a pioneer in doing what is always in retrospect obvious. You don't have to have an oxygen involving anode, but you can make the anodic reaction by dissolving deuterium into the electrolyte, as in a fuel cell. The fuel cell works that way. The fuel comes in and the H2 dissolves. You can do it with D2, so the current passes. The potential on the cell is now very, very much less. It's an interesting feature that wouldn't apply in palladium. Now the potential is the sum of the open potentials only. There's no reversible potential there at all. It's zero because well, there's just no pressure driving by the open potential. As to using palladium, yes, it's certainly an alternative. I think I prefer the fuel cell method because it now leaves you with a much less potential use position, and that indeed may lead to less ion problems.
Dr. Bockris, I do have a comment on the kinetics situation. This has got to be a time-dependent phenomenon as to what the kinetic situation is, and I was surprised that you missed out on mentioning that the state of charge of the electrode has got to determine what the kinetics is. It is very clear that the initial stages of charging the Rosky mechanism cannot be the slow one. You yourself mentioned, in fact, that initially it is the diffusion that is rate limiting, namely of the deuterium atoms into the palladium. And furthermore, we know for certain that in the initial stages of starting charging, there is no deuterium molecular evolution. So I think that your statements have got to be tied to the time element, namely the state of charge of the electrode. Secondly, your comment on the impurities. Yes, if we avoid the dissolution of the anode, that's the first important step to be taken. But it's only part of the way, because both of us know very well the standard techniques in electrochemistry that have to be applied in order to clean up the electrolyte itself. And the standard techniques, for those in the audience that are interested in this, are the following, namely redistillation, filtering. In fact, one has to start with filtering first because there are ion particles in the solution. Secondly, followed by redistillation in quartz. And thirdly, what we call pre-electrolysis, where one subjects the solutions to many hours of pre-electrolysis to clean out the ionic impurities. Thank you.
Yes, I comment that your remarks are well taken, and the only thing I would like to say about them is, of course, when you talk about charging the electrode, I am not talking about that state. I am talking about the state in which the charge is neither revolving. To our present views, the change in mechanism comes during that evolution at a certain open potential. rather than certain charge. The charge is related to the potential. We find it's when you get up there to 0.3 or so, you're going towards 0.6, that the change mechanism to the one corresponding saturation occurs. I'm glad to talk more about impurity matter, but just remember historically, electrochemistry was one of the main things that I started many years ago. And quite right, I don't want to repeat anything you said. There are enhanced methods of filtering the electrolyte at the present time, but what we have done in work in different fields where we need super pure solutions, dielectric saturation work, we used first of all the super filter, and then we used power distillation at 1,000 degrees, shooting water out a very long hole, about 10 feet high, which was really a condenser. We filled it then with platinum chips, or they were glass chips, evaporated platinum on it. And by the time we've done all that, we've got to make it in water. Of course, it was never let it touch air or anything like that, otherwise it was ruined.